Hello everyone. Today we are going to explore one of the most important but often invisible step in turning our code into an executable or running program. When we write a program, you think about syntax, logic and functions. When you compile it, compiler converts your source code into object code. But even after compilation, your program is not ready to run. There is a small but powerful bridge between the compiled code and the running program. And that bridge is made up by the linker and loader. They work silently behind the scenes, connecting and arranging your code so it can finally execute. Without them, even the most perfect program would just sit as an isolated machine instruction, unable to come alive. So, to understand what linkers and loaders really do, let's start with an example. Imagine you are developing a program that calculates the total marks of a student. Now, you decided to write it using three different files. Like one is say input.c, which is used for reading the marks, process.c for computing the total, and display.c for showing the result. Each of these files are compiled separately into their own object files like input.o, process.o, and display.o. At this stage, each object file has machine code for its own functions, but the files don't yet know where other functions are defined. For example, process.o might be calling function say read marks, which is defined into input.o. But since the compiler compiled them separately, it doesn't know where to find read marks. And it's just marks it as unresolved or undefined. So we saw that while talking about nm command or even readelf. Now comes the linker. Its job is to combine all these object files into one final executable file. For example, your a.out or say marks.exe for your Windows machine or Windows operating system. The linker connects all functions and variables correctly so that every function call finds its definition. It also includes any needed library code such as printf and scanf from the standard library. Once the linking is complete, we have an executable file, but that file is still sitting on the disk. The loader is the one who takes it from the disk, loads it into memory, sets up all the memory addresses, and finally tells the CPU start running the program. So we can think of it like this. The compiler translates your code into machine instruction. The linker connects all parts of the programs together, and the loader moves the program into memory and starts the execution. They work together like a production team. The compiler writes the story, the linker connects the chapters, and the loader turns the pages for the CPU to read. So, to really understand why we need linkers and loaders, let's look how memory management evolved. In the early days of computing, programmers had to manually assign the addresses to variables and instructions. For example, variable A might be at address 1000, function F might start at address 1100, array X might start at 1200. If a new variable was added or one instruction gets changed, they had to manually recalculate every single address. It was error prone and exhausting, like building a city with no map. Then came the assembler, which introduced symbolic names. Now, instead of remembering the numbers, programmers could write A equal to 10, and the assembler would assign addresses automatically. But there was still a problem. If two programs, say both assumed that they start at address 0, they would clash in memory. So to solve this, relocating loaders were introduced. Programmers could now write code as if it always started from 0. When the loader placed it in memory, it would adjust or relocate the addresses automatically. And finally, in modern systems, we use dynamic binding, where addresses are not assigned permanently. The operating system assigns them at load time or even during the execution, depending on where there is a free space. And this allows programs to share memory, use resources efficiently, and run simultaneously without interfering with each other. Let's understand the difference clearly with the real world analogy. Imagine you are organizing a music concert. The linker is the event organizer. They gather the musicians, connect the instruments, arrange the sequence, and make sure everyone knows their role or part. The loader is the stage manager. They prepare the stage, plug in the microphones, check sound levels, and finally say, let's begin. So in technical terms, the linker works at compile time. It combines all object files, resolves functions and variable references, and produces one loadable file. The loader works at runtime. It transfers the program into memory, adjusts any remaining addresses, initializes the environment, and starts the execution. So the linker builds the performance, the loader starts the show. The linker works in two steps called as two-pass linking to make sure no symbol or address is missed. In pass 1, it scans all object files and collects information about every symbol, function, global variables, constants, and notes where they are defined and where they are used. And this information is explicitly stored in its own symbol table. Now the linker goes back in pass 2, replaces symbolic names with actual memory addresses, resolve references, and adjusts all code and data sections. And this is called as relocation. So it's like writing a book. In pass 1, you list all the chapters and page numbers. And in pass 2, you fill the page numbers in the table of contents. By the end of second pass, the linker produces a single well organized executable file ready for the loader. So when we use some familiar functions like printf, scanf, or square root, we are not writing them ourselves. They come from the libraries. A library is a collection of pre-compiled code that can be reused by many programs. The linker automatically searches libraries when it finds an undefined symbol and connects the missing function. There are two main types: static linking and dynamic linking. In static linking, the linker copies the necessary code from the library directly into your executables. And this makes the program self-contained. But problem is it increases the size of executable. Now dynamic linking. The linker connects only references to the library. The actual library code is loaded at runtime when needed. This saves the memory and allows easy updates. For example, if your system updates the math library, every program using dynamic linking will benefit it automatically. So libraries are the ultimate form of a teamwork. Write once, use everywhere. So when we separate modules are compiled, they can't all start at the same addresses. But every one of them thinks they do. And this is where relocation comes into picture. The linker updates every memory address and instruction that refers to data or functions. So when the loader places the program in memory, all addresses are correct. Later, the loader may perform dynamic relocation, adjusting addresses again to fit available memory spaces. One can think of relocation like updating the contact numbers in your phone after everyone changes the SIM cards. The names remain the same, but the locations are updated. That is, addresses are updated to keep everything connected correctly. So when you run a single command like gcc say main.c, it feels like only the compiler is working. But actually, GCC is acting as a compiler driver. It controls a whole pipeline of tools. First, preprocessor, which expands macros. Then comes compiler, which translates code into assembly. Then comes assembler, which creates object files. And lastly, linker joins everything to create an executable. So one simple command runs a whole sequence of steps automatically. Generally, advanced developers use linker scripts to fine tune memory layout. For example, deciding where code, data, and stack segments should go in embedded systems. This level of control is useful when every byte of memory counts. And now, let's step back and appreciate it as a bigger picture. Every time you run your program, whether it is simple calculator or a large software system, the linker and loader are working silently in the background. They connect your code, arrange its structure, and breathe life into it. Without them, even the best code would remain static, a pile of machine instructions with no movement or purpose. So when you see an undefined reference error, that's the linker's polite way of saying, I'm missing a connection. Please give me the missing function. So when your program loads instantly, that's the loader doing the job efficiently. So remember, the compiler translates your ideas to code, the linker connects your logic into structure, and the loader brings the structure to life. Imagine your program as a grand orchestra. The compiler writes the music, the linker gathers all instruments and tunes them, and the loader raises the button and starts the performance. Without any one of them, the music of your program would never play. So next time your code runs smoothly, silently thank the invisible architects, the linker and loader, the engineers who turn your logic into the life. Thank you.